Welcome to Anatomy and Physiology.
Okay guys, Dr. Sean over at Fortis Colleges. We're going to go over, as you can see up through whatever, over here, up through here, there, kind of stuff, is the OAHP 106. That's going to be, where are we, right up in here where you can see the underline. And right there, and we're going to go down here to the Vital Source bookshelf, and we're going to look at the book, and I'm going to go over some of the stuff that we need to know. Now, I'm going to be looking both at you guys and at my screen. We use cookies. Yeah, sure, fine. Mastering Healthcare Terminology, that's not the book we want. We want this one here, Human Health, Body and Health and Illness. That one, it says continue reading. I really don't like that part, but you know, hey, it is what it is. We get what we get. We're going to look through. You can see the entire thing here. I've got my entire, let's see, OBS Studio. This is the other stuff for the class. Stuff open up there. Hopefully you guys are in the same thing. This is chapter 2. We're going to start right on these things and go through basically the entire chapter. I'm kind of going to read it to you and explain things as we go through. So the objectives of this class: define the terms matter, which means actually things that have weight and take up space. Like me, I matter because I weigh something quite a bit actually, and I take up space. Elements are what we make up the entire universe of these certain elements, which those eventually make molecules, right? And then we have atoms. Atoms make up molecules. So atoms are the smallest bit we have, based on atomos, which means not able to cut anymore. Now, of course, now we have things like quantum physics and all kinds of other physics and the Bohr model and all this kind of stuff. So we have electrons and neutrons and protons. We'll get into those too. And do the following. Let's see. List 4 elements that compose 96% of the body weight. First guess: oxygen and carbon, and then the other one's going to be hydrogen. So that's at least three of the elements right there, and probably nitrogen, I'm going to guess, is the 4th one. Describe the 3 components of an atom. We just said that, right? 3 components of an atom. An atom has 3 parts. I wish I could draw these for you, but I don't have that figured out yet. I haven't quite figured out how to do the drawing on this thing up here, this thing here. So an atom has 3 pieces. It has the main part, the center of it, which is like the nucleus, and then spinning around it is an electron, and those are negatively charged. And inside the nucleus, there's 2 bits in there, the neutrons, which have no charge, and the positrons or protons, which have a positive charge. Okay, so we go through these here. Describe the role of electrons in the formation of chemical bonds. Okay, so that's going to be a little bit more detailed, and we'll go through that on the book itself. So I've got to get like a timer or something going on here. It's 15:21, so 22. Difference between ionic, covalent, and hydrogen bonds. Oh, that's fun. Explain ions, including the difference between electrolytes. Cations. Cations are negative, and anions are positive. But let's get to that in a minute. Explain the difference between that determines the cations and anions, determines the direction that things usually move. Okay, and how they attract each other, like opposites attract, right? Explain the difference between a molecule and a compound, and 5 reasons why water is essential to life. Water. It's essential to life. Explain the role of a catalyst and enzymes. So, easy peasy on catalysts and enzymes. Enzymes are always proteins. Your body makes enzymes. Your body makes proteins out of amino acids. We talked about that a little bit before in another class, but we'll go in one of the other sections. So, amino acids, which are little chains of things with carbons and hydrogens and nitrogens and sulfurs and stuff like that. There's certain ones that are essential, and there's certain ones that are non-essential. The ones that are essential you got to get from your diet, and the ones that are not essential your body can make if it has all the stuff. So you make proteins, which are enzymes. Enzymes help things occur. They have a very specific kind of lock and key kind of mechanism, so they don't work on everything, okay, generally. Now, a catalyst, let's think of a catalyst as, let's say I put in some dye into my bottle of water. You can see it's kind of clear right here, but you put a little water, dye in there, and it all comes down and settles on the bottom. The catalyst is something that makes this reaction of that spreading out and becoming completely blue or whatever by me shaking it up or using a spoon. The spoon would, for example, be the catalyst, something that changes the reaction time. Okay, generally those things, it's already going to happen, but it's going to happen faster. Okay, like when you pour milk in your coffee and you don't stir it, and it just kind of sits there and it's not quite, some of it's not as creamy as the other sides and not as sweet because the sugar didn't get mixed. And you got to mix it. That's what that means. Differentiate between an acid and a base and define pH. pH, notice it's a small p and a large H. H is because it's a potential of hydrogen, capital H is a proper noun, to do something. Okay, to receive or give electrons, and we'll get into that in a minute. List the 6 forms of energy and describe the role of adenosine triphosphate in the energy transfer. The ADP in energy transfer is an energy transfer. We'll talk about that because we're going to get back into things like the mitochondria, remember the powerhouse of the cell, and the pyruvate cycle and some stuff in the cytoplasm, so we have to use our Wayback Machine to remember some of that stuff. Differentiate mixture, solution, suspension, colloidal suspension, and precipitate. Okay, so here's the cool terms. As you go down, you can actually look at any of these, and here, look, you can go like this, and it'll take you right to the same question, to the chapter. It'll take you to the page. So here you go. Forms of energy. There's the forms of energy. We have nuclear energy, thermal energy, that's heat, right? Radiant energy, energy that travels in waves. Electrical energy, chemical energy, and mechanical. So let's go all the way back here. It says all the way up, and we don't want to do that. Let's go to the beginning of the chapter. Can you begin the chapter? No, we don't. See, this is the hard part about this. Major organ systems. What the heck? This is one thing I don't like about this book. It's kind of hard for me, anyway, to do the travels. Wait, I don't want this. Update our read feature. I don't want to do that. How do you get rid of that? There we go. Go to chapter 2. I'm just going to scroll down until I find it again. Yeah. Next chapter, maybe? Yeah, I don't like this. See, kind of a pain. It's a pain for everybody. This is why, guys, I want you guys to get the actual book. This is the fifth edition of the same darn book. So if I look in here, I can go to chapter 2 by flipping pages. It's pretty freaking easy. And then I can write my little own notes wherever I want to. So here you go. There's some pictures that just should be just like in the book. Get your own book. It's much easier that way. Now, each one of these, we can go through each one of these little, say like here's matter or mixture or whatever, and it'll tell you what page it's on. And so that gives you a chance. You can use it when you're doing the quiz or when you're doing a test. You can kind of look things up from there. Suspension evil is a Herlihy why a chapter on chemistry because our body's made of chemicals. Okay, whatever. So basically, chemistry is one of the 3 main things that make up your body. Okay, if we're thinking about it. So we have like the mental, emotional, spiritual energy. That's one section. And we have like a physical energy or physical structures and stuff. And then we have chemistry, which is kind of like what happens, how we get around and what we're made of. Now, chemistry really bubbles over all of them because as we're looking here in biochemistry and organic and inorganic chemistry. So what does organic and inorganic mean? Organic means that it has 2 main things. Carbon and hydrogen, whatever. So it has carbon and hydrogen, C and H. The way I remember it, back in the old days, we had this stuff called C and H sugar, and that's the only way I can remember it. It's organic. It was grown in the sun from Hawaii, blah, blah, blah. They don't advertise that kind of stuff anymore. I don't know why. So, so we have organic versus inorganic. That has nothing to do with how it's grown, really. This is different. This is science. This is, what's it called? Not science. This is science. This is, what? Physiology, man. Okay, why a chapter on chemistry? Chemistry matter is anything that occupies space and has weight. That's what we said, okay? Hopefully you wrote that down. Matter exists in 3 states. There are other states now because they say there's a solid, okay, which is like ice, and a liquid, which is like water, and then there's a gas, which is like steam, right? But then there's like a plasma state of it. So at this point, at least we have those, okay? So we can basically ID which ones we are in each of those. Blood is in kind of a couple states. It does have a solid portion, which is the whole blood, and then it has the liquid portion, which is called the plasma. That's important to understand later on. Saliva, digestive juices, yada yada. There we go. Okay. Oh look, there we go. So it changes in matter. So you can chop it up into smaller pieces, or you can burn it and turn it into chemical energy. Use chemical energy and thermal energy to change the state of it and oxidize or change the oxygen and carbon balances in that same thing. They're still there. They're just moved around. The other thing with most energy is, like we know, energy cannot be created, nor can it be destroyed, but it can change its shape and change around. Same thing with matter, really. Matter really can't be destroyed. It has to be moved from different places to different places. Okay, we don't usually end up with anything less. Elements, elements is matter that is composed of atoms. Why Why children should not be able to play in traffic and chew old paint. Well, playing in traffic is probably a bad idea. But see, one of the old things that they talk about chewing paint. Kids used to eat paint chips, and that would give them a lead poisoning because lead was a component in the paint as well as in gasoline to help it work better. Now in gasoline it prevented some knocking in the engine, and in paint it helped it stick a little bit better and more smoothly. Now if you have a really old house, you can go find some of the paint that's peeling like on the windowsill, and you peel it up and it'll look kind of silver on the back. That's probably lead. Don't eat it. But kids would want to eat it, and one of the things that happens when kids eat that stuff, for some reason, a reason they call it pica, P-I-C-A. Pica is when you want to eat dirt and you want to eat minerals or you want to eat something that isn't food. Okay, it's called pica. It happens to like pregnant women. They want to eat dirt for some reason. They're like, I don't know why. It means they have a mineral deficiency, and they're trying to pull in those minerals some way through that innate internal intelligence. Their brains are going like, I need something, man. I got to eat some rocks. Calcium, magnesium, etc. So little kids can have that same thing. When they start eating this, that lead gets into the bloodstream and it settles in different areas. You can see it in the fingernails, you can see it in the bones on x-ray, and you can see it in the gums. It'll be like a grayish silver line up in there. It's very, very bad. Like mercury does the same thing. You've heard of Mad Hatter? He was a guy who used mercury, because it's a liquid form of metal, and he would have these felt, like a felt mold for a hat, like a certain kind of shape of a hat, right? And he put felt on that in that little metal mold, and he'd pour like this, and he would pour mercury, right? And it'd go inside there, and it would hold the shape exactly as the thing, and he would just let it set, and then it would kind of like set in that shape. He'd dump that mercury out, and then you'd be okay. But if you get it in your little tiny cuts, like I have a little tiny cut on my finger, if you get it in your cuts, it gets in your bloodstream, causes neurological problems, and it makes you blah, blah, mad. Okay, there we go. So also, of course, lead's used in pipes, and that's not good. We did change some of that stuff, I hope. You know, like not like in Michigan, I think it is, somewhere up there. Okay, most of the elements, carbon, hydrogen, oxygen, and nitrogen make up 90%, 6%. That's what we said. That was good. Okay, atom structure. Atoms have those three things. Electrons negative. Okay, if you're writing this down, electrons have a negative charge. Protons have a positive charge, and neutrons have no charge at all. So a proton and a neutron walk into a bar and they order drinks, and the bartender says, proton for you, it's going to be $1, and for you, neutron, no charge. Because there's no charge, right? Stupid, but you remember. Here's the other ones. There's about 33, I think, different minerals that make up the body, and there they are in this list here. So we have things like chromium, copper, fluorine, zinc. Zinc is very important for like creation of proper hormones and sperm production and estrogens and testosterones. Copper, fluorine. Now we see fluorine. Fluorine is used for different stuff. It isn't for your teeth. Fluoride and fluorine are actually neurotoxins. If you get too much of them, we don't want to have too much. It's not really good. Now, calcium, that's what good for your teeth right there. Like number 5. Okay, nitrogen is kind of it's a gas. It doesn't really make a big difference in a lot of stuff physiologically, but it's used in everything. Okay, it's a very big connector for a lot of things, like oxygen and carbon. Those are really good connectors for some things. Nitrogen is a gas that if you're breathing regular air, it's part of the air that we breathe. Actually, it's about, I think, 70% of the air we breathe. Only about 20% or 18% is actually oxygen, and the rest is carbon dioxide and some other gases that float around out there. It's an amazing, weird thing, right? You didn't think that nitrogen was that big. When you go and scuba dive, you breathe that stuff in, and the nitrogen doesn't change over in the cells like oxygen does. It's not even used. So it just hangs out and moves around. But it can collect into bubbles if you come up from the surface too fast and you have a little tiny bubble in your system, and then when you rise up to the top, it's a big bubble and you have an aneurysm basically. Okay, let's go down for the next one. Here we go. Very important concept here. Isotope. That's what it says. Isotope. A different form of the same atom. Any old atom can have an isotope. Hydrogen has different forms. Atomic number of 1, you can have heavy hydrogen, you can have heavy oxygen, you can have heavy water actually. It takes heavy isotope of oxygen. Remember, an isotope has the same atomic number as atom but different atomic mass. So any molecule or any atom that has a different mass than the atomic number. So generally, the atomic number is the number of protons, right? And the atomic mass or the atomic weight is the number of protons plus neutrons. So let's say hydrogen, which is supposed to have one, or let's say oxygen, which is supposed to have eight protons, and normally, when it's super stable, has 8 neutrons, and it has 8 electrons on the outside. That's a very balanced little atom. If it's an isotope, it might have a little bit different in here and there. Okay, it usually is some kind of different thing. They're unstable, and their nuclei break down. They give off energy when they decay. Okay, in doing so, the unstable nuclei become more stable. So they try to get to a more stable state. Everything's trying to get to that like base matter. That's kind of called chaos or like entropy. Really, everything's falling apart, even us. Unstable nuclei become more stable. Unstable isotopes are called radioisotopes. Process of breakdown and decay is called radioactivity. Okay, so we know what all that is. We use like here, for example, radioactive iodine is used to destroy excess thyroid tissue. So radioactivity, like nuclear radiation, we're talking like isotopes and ionic radiation, that can cause problems in DNA, and it can also kill your nucleus and keep your cells from growing. So fast growing cells, mucous membranes. We talked about membranes already too, I think. So or maybe we're going to talk about it later. Mucous membranes, right? There's serous membranes on the inside, and there's synovial membranes on the inside here. Membranes have to rebuild and repair very often. If you kill the nucleus or damage the DNA, which is the guidebook on how to build new proteins, which is part of its structure, then what happens is it breaks down and starts falling apart. So people that get radiation poisoning, full body radiation poisoning, will end up having bleeding gums, maybe bleeding from the eyes, bleeding from the digestive openings, okay? And it's a very bad deal because they start like coughing up blood and things. And that's the inside mucous membranes all the way in through the lungs and in through the stomach and everything, breaking down and not repairing themselves. So you get a lot of lesions, which are like sores, and those start to bleed, and that's how you expire. Now, the thyroid, which is a gland that's right here, okay, is very, very important for metabolism. Think of it as your thermostat. Remember, so I'm going to bounce around a lot in our lecture here because I want you to see the connections that are made between chemistry and physiology and anatomy and all the different crazy parts. Because some of the things that happen in this book, okay, that you guys get in this book, is it'll give you some case studies. You'll notice the case studies are really like diagnostic, and they have a lot to do with medical procedures, which you're not going to be doing, right? So it'd be better to have different versions of those, but we need to like start making our brain have those connections, okay? So the thyroid, if it doesn't have enough iodine, okay, if you don't have any iodine, you can get a goiter. That's like a swelling of this thing here, and it can look like bad. It can become cancerous. You can have to have that removed. There's all kinds of problems. And iodine is actually protective of radiation. It's weird that this gland that's here is under such thin skin, and you think it'd be somewhere deep inside if it was so radioactively sensitive, but it's not. So it's right there. Okay. There we go. So here we have some different ideas of the atoms, and they're using this example up here of the sun. So the sun is like the nucleus, and then you have these guys around the outside. Those are the, what are those called? Electrons, okay? Here we got nucleus. You have different shapes of everything. So there we go, protons, neutrons. And there we go, we have again our ability to understand that neutrons are neutral, have no charge. Protons are positive, they have a positive charge. And electrons are negative, okay? What's the difference between the atomic number and atomic mass? We talked about that. Atomic number is the number of protons. That's it. The atomic mass is the number of protons plus the number of neutrons. Okay, so there's many different things. There can be a lot of different. Generally, when they're super stable, they're equal. Okay, so like, let's see if I can find it. I think in here we have a periodic table. If we don't, you're gonna have to look one up. I do not see a periodic table. So maybe put it in the back. No, we don't have a periodic table. I have other books sitting over here. Let me see if I have this one. Principles of Anatomy and Physiology. Sorry about that. That was terrible. I just lost all of my stuff here. What happened? Ah! My screen fell. Where are we at here? Ah, come on, man. This is way back there. What's this? Chapter 2. Come on. Oh, come on, man. See, annoying, man. Basic chemistry. Here we go. Let's go hunt down where we were. In here. So, I don't think I have actually one of those charts. Sometimes they'll put them in the back of certain books. But anyway, you've seen the charts. Come on, man. This is a good old book. Organelles, cell division, cancers. Well, I can't find it right now. I'll have to look for it later. Sorry about the fall there. That was crazy. Everything moved and this thing fell. I just kind of have it like set up there. I know it's not a great thing to do, but it is what it is. Okay. Electron shells surround the nucleus orbits called shells. Okay, so you have the nucleus in the middle, and then there's like these little orbits around the outside. They're three-dimensional, so they're going all over which way. Now, the other weird thing about it, if you get into physics too, is they kind of like exist, and then they don't exist depending on if you're looking for them. Chemical bonds. Atoms are attracted to each other because they want to achieve a stable outer electron shell. We're going to get into that in a minute. Now, there's certain shells or layers, orbits, right? The first one can hold 2 electrons, and if it only has 1, it's trying to look for another one to make it feel stable again, right? And the next one has 8, and that one may have 6, so it's got to look for 2. You know what I mean? And it keeps going out like that. They want to achieve a stable outer electron shell. In other words, they want to fill or empty the outer electron shell. Well, they want to fill it, what they want to do. Okay, the force of attraction between the atom is similar to the force of 2 magnets. Negatives. Okay, so if you have one atom that has less electrons and one that has more, they're going to be attracted to each other because they want to even each other out. Okay, that's a chemical bond. Now, the ionic bond is caused by a transfer of electrons between atoms. That's those shells again, right? Interactions of the sodium and chloride atoms, sodium, chloride. Sodium is Na, it's natrium actually, and it's a little plus. And chloride, which is chlorine, like chlorine gas, which is poisonous. Sodium is like a little metal. It's like a butter, not flavored, it's butter texture metal. And as soon as it hits air or water, it catches fire. And then chlorine, if you breathe it in, you die. You put them both together, it makes table salt, which makes your body saline, which makes you easier to survive because you need to have saline. We're basically big bags of salt water walking around on land trying to do stuff, I guess. So here the sodium ion, okay, atom has 11 protons in its nucleus and 11 electrons in its shell. Remember, those should be equal. 2 electrons are in the inner shell, 8 in the second shell, and only 1 in the outer shell. This single shell makes it unstable. It wants to have more than that. Okay. Sodium often bonds with chlorine. Okay, chlorine is the same kind of deal. They connect together. A negative and a positive connect together, and they make a more stable element, basically. Okay, or NaCl, which is called table salt. Covalent. Covalent. Co meaning like to share, like cohabitate. We live together. Cooperate. We do something together. Right. Those are cooperation. Combobulate. I don't know. Whatever. So covalent bonds. Valence is just another word for those orbits around the atom. So remember, I had the nucleus, then we have these little orbits around it. There's many of them, and those are called valencies, okay, or a valence, and they're covalent. You share those. The second time is called covalent bond. It involves sharing electrons by the outer shells of the electrons. It's like joining hands. Now look at the difference here. So you may have the same thing. It's difficult to tell which one's which. Okay, and we'll get into that in a little bit. I'm going to do a whole thing on that. Hydrogen bonds differs from ionic bonds because it's hydrogen, basically. Electrons, the outer shells, atoms. Atoms are illustrated by weak attraction to other water molecules. This kind of, okay, here we go. Yay, look, there's a whole thing there. Look at this little picture here. You can look stuff up on YouTube. It'll have a better explanation than I can do on these because it's kind of crazy. Water engages in hydrogen bond because it's a polar molecule. Molecules have a polarity, which means they're basically kind of magnetic, okay? The water is a slight negative charge on the oxygen end. Yeah, that's what it turns out to be. And ions, cations, anions, and electrolytes. Several other terms are related to the activity of electrons in the outer shells of the atoms. If the negatively charged electrons are lost, okay, because if the electrons go away or gained by the outer shell of an atom, the electrical charge of the atom changes. Here's how it works. If it's completely a neutral charge, then basically it has the exact same number of protons and neutrons, because positive and negatives, they cancel each other out, right? So you have one proton, which is positive, and one electron, which is negative, and those two hang together and they just kind of bloop and they hang on, and that's it, they're done. Now, if you have one proton and two electrons, the electrons are negative and protons are positive, it's going to be a more negative ion. If you're going to have two protons and one electron for some reason, then you're going to be more positive, right? That makes sense? Okay, so that's how it's going to be. Up here, look at the electric charge of an atom changes. In other words, the electrical charge of an atom changes from the neutral charge, no charge, to a positive charge or negative charge. Atoms that carry an electrical charge are called ions. Okay, so they become an ion of whatever it is. If the ion is positively charged, it's called a cation. Remember, cation means it's cat, like C-A-T. The T is a plus. It'll remind you that. And an anion is negative. And that has a difference between how it moves in electricity, but we'll get to that some other day. Electrolytes, you heard electrolytes, right? Those are in like Gatorade and stuff like that. And those are your like baking soda and your salt and your sugar, and those things have electrolytes, which are different minerals. Look here. Electrolytes is a substance that forms ions when it's dissolved in water. Very good point. Water is important. You have to have electrolytes only about water. As the name implies, they're capable of conducting electrical current. Okay, so which most of your minerals will help you do. Okay, if you put more baking soda in water, which is sodium bicarbonate, then you get a much better electrical current through the water. If you have salt in there, an amazingly good electrical current through there. We work on that, kind of like our bodies work on that. And the same thing is if you get hit by lightning, which don't do. Okay, ions are formed when electrons in the outer shell are lost or gained, so they're unbalanced. For example, sodium ion has positive 11 electrons, positive charge and 11 electrons, negative charge. If a single electron is donated, the sodium is left with 11 positive and only 10 negative. Therefore, it would be positive because it has more positives than negatives. Does that make sense? What does it say? Chlorine has 17 protons. Okay, whatever. That's okay. You got that one. Ionization. When an electrolyte splits or breaks apart in solution, like water, electrolyte is said to dissociate. For example, sodium chloride, NaCl, sodium natrium chloride. So natrium is the old word for sodium. Okay, is an electrolyte. In the solid state, it appears as tiny white granules. Big chunks it can be in. Salt is a big giant crystal, and you grind it up and you make little tiny granules, and then you put it on your soup or whatever, your noodles. Okay. When dissolved in water, the salt dissociates. What is happening? It dissociates. It breaks apart. It really doesn't. I mean, it still stays in a solution, and that solution being water, it makes basically salt water. You can still taste it that way. Okay. Sodium function, fluid balance. Okay, so here, this is actually really good. So these are the main ions that we have, the cations versus the anions. Remember, cations are positive. You can see right here, look, little positives on the end of each one. That means it is positive. So that means it has more more protons than it has electrons. Okay, and we're going to probably stop this section right about here because we're going to start again with compounds in a minute. So, but let's see, ionization. When electrolyte splits, it breaks parts in solution. These are all the cations. Sodium, calcium, iron. Iron, so it's Fe, it's so different, right? Ferrous, all right? Hydrogen, potassium, this is kalium, is what the word was for that one. And then ammonium, or ammonia, okay, more acid-base regulation. This has to do with the way you break apart proteins. Okay, chloride, bicarbonate, and phosphate. These are good to understand that they're part of it. At least if you understand and recognize when you hear those, you're like, hey, that's part of the body, and you recognize it's something that isn't part of the body. Like here we have uranium, shouldn't be part of the body. Okay, here we go. Sodium chloride becomes sodium ion and chloride items. They weaken the solid ion splits into sodium and chloride. The ionization. It usually takes electricity to do that kind of stuff. Let's see. This medical jargon for electrolytes, one of the most important clinical tool is the assessment of patient electrolytes. So when you take blood tests, we're looking for electrolytes as well. And sometimes with like urine tests as well. So we're looking for sodium, potassium, chloride, magnesium, and bicarbonate. Now, what those do in the body is they help maintain a pH balance, which we're going to get here in a minute. Okay, so here we got all these sodiums and water and all this kind of fun stuff. Molecules and compounds. I want to see how far we're going to go because we're not going to go too much into this. I want to go into other stuff. So there's acids and bases. Okay, we're going to talk about oxygen and compounds after this. So this is just the first part of that chapter 2. Hopefully that was useful. Go ahead and take some notes on this kind of thing. Remember, when you're on YouTube here, you can always go back and reread something or relook at something. And then you can also speed it up so that you can put it at 1.5 or something and make me talk faster. Okay? So you guys, don't forget to do your homework. This is all conceptual stuff. We're trying to get as much as we can into your brains as possible. And by doing that, we will stuff your skull, basically. Okay, so let's go over here. I'm going to see if I can find my way out of here. Where is my... There we go. And I'm going to stop that recording. And we'll talk to you guys on the flip side, next part of Chapter 2. Okay, this is Chapter 2, Part 1.